Welcome to another JPJ Discovery video. Today's topic is, how long is a second? From the beginning of the universe to the present day, time is one of the few things we regard as regular and unchanging. Time works by measuring periods between the past, present, and future. But that's a simple, albeit vague answer to an incredibly complex topic. But time is not as constant nor as simple as it may seem. In the 17th century, physicist Isaac Newton saw time as an arrow fired from a bow, traveling in a direct, straight line and never deviating from its path. To Newton, 1 second on Earth was the same length of time as that same second on Mars, Jupiter, or in deep space. He believed that absolute motion could not be detected, which meant that nothing in the universe had a constant speed, even light. By applying this theory, he was able to assume that if the speed of light could vary, then time must be constant. Time must tick from 1 second to the next, with no difference between the length of any 2 seconds. This is something that it's easy to think is true. Every day has roughly 24 hours. You don't have one day with 26 and one with 23. However, in 1905, Albert Einstein asserted that the speed of light doesn't vary, but is a constant, traveling at 186,282 miles per second. Einstein postulated that time was more like a river, ebbing and flowing depending on the effects of gravity and space-time. Time would speed up and slow down around cosmological bodies with different masses and velocities, and therefore 1 second on Earth was not the same length of time everywhere in the universe. Decades later, Einstein's theory was proven to be true. In October 1971, physicists J.C. Haffel and Richard Keating tested Einstein's theory by flying 4 cesium atomic clocks on planes around the world, going eastwards and then westwards. In their paper published in 1972 in the journal Science, Haffel and Keating reported that the airborne clocks were about 59 nanoseconds slower than a ground-based atomic clock when traveling east, and 273 nanoseconds faster than the ground-based version when traveling west. Their results supported Einstein's theory that time fluctuates throughout the universe. There are 2 main ways of measuring time, dynamic and atomic time. The former relies on the motion of celestial bodies, including Earth, to keep track of time, whether it's the rotation time of a distant spinning star such as a pulsar, the motion of a star across our night sky, or the rotation of Earth. However, a spinning star notwithstanding, these methods are not always entirely accurate. The old definition of a second was based on the rotation of Earth, as it takes the sun one day to rise in the east, set in the west, and rise again. A day was almost arbitrarily divided into 24 hours, an hour into 60 minutes, and a minute into 60 seconds. However, Earth doesn't rotate uniformly. Its rotation decreases at a rate of about 30 seconds every 10,000 years due to factors such as tidal friction. Scientists have devised ways to account for the changing speed of Earth's rotation, introducing leap seconds, but for the most accurate time you have to go even smaller. Atomic time relies on the energy transition within an atom of a certain element, commonly cesium. By defining a second using the number of these transitions, time can be measured with an accuracy of losing a tiny portion of a second in a million years. The definition of a second is now defined as 9,192,631,770 transitions within a cesium atom. By counting 9,192,631,770 of these microwave cycles, scientists can define an exact 1 second interval. Atomic clocks provide the most accurate track of time on Earth. The entire GPS system in orbit around Earth uses atomic clocks to accurately track positions and relay data to the planet, while entire scientific centers are set up to calculate the most accurate measure of time, usually by measuring transitions within a cesium atom. While most atomic clocks rely on magnetic fields, modern clocks are using lasers to track and detect energy transitions within cesium atoms and keep a more definite measure of time. Although cesium clocks are currently used to keep time around the world, strontium clocks promise twice as much accuracy, while an experimental design based on charged mercury atoms could reduce discrepancies even further to less than 1 second lost or gained in 400 million years. Although Newton and Einstein came up with conflicting theories to explain how time works, both scholars agreed that time moves only forward. So far, there is no physical evidence that anything in the universe can dodge time and move backwards nor jump ahead. And scientists aren't entirely sure why time moves only forward, but they have theories. One theory relies on the second law of thermodynamics. This law states that everything in the universe tends to move from low to high entropy, or from uniformity to disorder, beginning with simplicity at the Big Bang and moving to the almost random arrangement of galaxies and their inhabitants in the present day. This is known as the arrow of time, or sometimes time's arrow. Another theory suggests that the passage of time is due to our expanding universe. As the universe expands, it pulls time with it because space and time are linked as one. But this implies that if the universe were to reach a theoretical limit of expansion and begin to contract, then time would reverse. A slight paradox. Could time really move backwards, with everything coming back to an era of simplicity and ending with a big crunch? It's unlikely we'll be around to find out, but we can postulate on what we think might happen. Subscribe and stay tuned for more videos. Thanks for watching.